Hey everyone. Today we're going to talk about extreme values of functions, which is section 4.1 in your book. We're going to start off by talking about examples 1 and 2. So there are a few different types of extreme values of functions. We can have a max or a min. So a maximum value for the function or a minimum value for the function. And of those two types of extreme values, they could be designated as a local maximum or a absolute. Same thing for the minimum. So the minimum could be a local or a absolute. As an example, let's look at a function like cosine. So cosine starts at 1 at 0, and then it approaches 0 at the value pi over 2, and it approaches 0 at the value negative pi over 2. In this case, on this domain, so if our function f of x is equal to cosine x, and our interval is inclusive, negative pi over 2 to pi over 2, then the point at 0, the value 1, is an absolute maximum. And it's an absolute maximum because there are no other points on that interval that have a greater value. Negative pi over 2 and pi over 2 are local minimums. And it's a local min because there are other points that have a value either the same as that or lower. So in this case, the lowest value that the function takes on in the domain is 0. And since there's two places that happens, those are our local minimums. If we were to consider another function, say sine, from negative pi over 2 to pi over 2, sine starts at 0 and approaches a maximum value of 1 at pi over 2, and it approaches a minimum value of negative 1 at negative pi over 2. So if our function is g of x equals sine of x, and our domain is again negative pi over 2 to pi over 2, then our function has an absolute max in this domain, which is 1, and it has an absolute minimum which is negative 1. Another word for absolute is global. So you might hear the book reference absolute or global. So those mean the same thing. It means that anywhere on the domain given, there isn't anything that's either greater or less than that number. So the absolute max would be the biggest in the domain. The question is, what about a function that takes on multiple values? So let's say that we graph sine from, so in this case our function g of x is equal to sine x, and our domain now is 0 to, let's just do 0 to what is this, 5 pi over 2. So in this case, we have two places where there's a maximum and we have one minimum down at the bottom. So if our interval includes all of those numbers, then again, these two values are not absolute. This is just a local max. This is a local max. We do have an absolute min sitting down there, since there isn't anything on that interval that is less than -1. Another word for local is relative. So you might hear that referenced as relative. So let's look at the function y equals x squared, and let's define the domain in different ways. So first, if we have a graph of y equals x squared, and the domain is all real numbers, then the only thing we can say is that there's an absolute minimum. In that domain, there are no values of the function that get less than 0, so this is an absolute minimum. We could define the domain differently. We could define the domain as being 0 to 2 inclusive. So we would have that. And in this case, we would have an absolute minimum and an absolute max. This would be our absolute minimum, and this would be our absolute max. If we defined the domain slightly differently, say with a non-inclusive point, so the domain was not including 0, then we would have an open, non-inclusive point here, and a closed point here. So in this case, there is only an absolute max. And there is no min. There's no local min, and there's no relative min, or absolute min. No minimum. And the reason for that is that the lowest point, 0, doesn't exist. And all the points that proceed before it can be taken arbitrarily close to 0. So it doesn't make any sense for us to list a minimum value, because we could always list a value less than that. Something closer to 0 than the number we just picked. And that's always true. It's infinitely divisible as we try to approach 0. But 0 is not included, so we don't actually, we can't pick that number as our minimum. So if you have a non-inclusive point on an endpoint like that, it's not counted as one of your extreme values. So if both are non-inclusive, so let's say that I have the domain is equal to 0 to 2 non-inclusive, this has no extreme values. Or the plural of extrema, or extreme values is extrema, so we could say no extrema. And just like the logic from before, we can get arbitrarily close to 0 or arbitrarily close to 4, so there isn't any defined maximum or minimum value on that interval. You can read more about that is the extreme value theorem, which is Theorem 1 on page 178. Alright, so there's one other graph in the book. Let's say we have some random function that looks like this. So in this case we have several different extreme values. In this case, the point up here, this is an absolute max. There's no other point on this interval shown that is any greater than that. This point here is a local min. On a small interval around that point, everything else is larger than it. But there is another point that is smaller. So this is our absolute min. And by the same logic, this would be a local max. On a small interval around that critical point, around that extreme value, everything else is smaller, so it's a maximum, but it's not the largest value on the interval. And so this also would be a local min. Altogether, these are called the extreme values of the function, and the plural of that again is extrema. One interesting bit to note is that an absolute extreme value are also local. So if the book asks you to list local extrema, they want everything. If they want you to list just the absolute extrema, you should just list the absolute. So we can think of absolute as being a subset of the local or relative extrema. Another interesting thing, and this is Theorem 2 on page 179, is that all of the extreme values that appear on the interior of the interval have a derivative that is either 0 or undefined. So in these first two examples here, f prime is equal to 0, f prime is equal to 0. I can also have situations where I have a max or a min at a place where f prime is undefined. So Theorem 2 in your book says that any critical point occurs where f prime of some value c is equal to 0 or undefined. and that's a critical